Hello, dear Kia family members. First of all, on behalf of Kia management, I would like to thank you for your continued effort for the globalization of Kia Motors with quality after-sales activities. This videotape was produced for the purpose of service training on the Opirus. This videotape contains engine, automatic transaxle, chassis, and electrical. Let's start with the engine system applied in the Opirus. The Opirus adopts Sigma's 3.5-liter V6 DOHC engines, which are similar to the Sorento 3.5-liter gasoline engine. Now, let's take a look at the major characteristics of the Sigma 3.5 engine. The Sigma 3.5 V6 DOHC engine uses a Melco EMS system, which has been used in the Optima 2.4-liter and Sorento 3.5-liter engines. Let's review the major differences of the Sigma 3.5-liter from the one used in the Sorento. The Opirus has a front-engine, front-drive type installation. The electronic control variable intake system, EGR system, Smartra standalone type immobilizer, and the newly adopted electronic throttle system. Now, let's move on to the timing belt. The Opirus timing belt, one cogged tooth timing belt, drives 4 sprockets and the water pump, and is kept under proper tension by a hydraulic auto timing belt tensioner. When assembling an engine, be attentive to the following. Install the timing belt using the marks on the right or left side of the bank. Install camshafts not by the machining mark, but by the identification mark, and also the intake and exhaust sides of the cylinder heads. Now, let's review the major components. First of all, a 16-pin data link connector, RCT connector, passenger side junction box, antenna unit and BCM are installed in the passenger side compartment. Major items installed in the engine compartment are the ETS assembly, 20-pin data link connector, junction box, APS, ETS relay, ignition failure sensor, and map sensor. For communication with diagnostic tools, a 16-pin data link is mainly used, and an RCT connector is used for ECM ROM data changing and basic ignition timing checks. To check the basic timing ground, the RCT pin number 3 is normal if the timing is 5 degrees plus or minus 2 degrees before top dead center when checked using a timing light. Now, let us review the major inputs and outputs of the engine. As for the major inputs, there are the oxygen sensor, Hall type CKP and CMP sensor, MAF and IAT sensor, TPS, ECT, knock sensor, ignition failure sensor, MRS motor rotation sensor, and power steering switch, and the EGR valve, injector, PCSV, and VIS are the main outputs. The ignition failure sensor is used to supply power to the ignition coil and to detect mainly secondary misfiring. Synchronizing waveforms through the CKP and CMP are as follows. It cannot be started if either the CKP or CMP has a failure. Zirconia-type oxygen sensors are used for front and rear. Here are the basic engine RPM and ignition timing specifications under normal conditions. The overrun fuel cut limits engine RPM to 4,700 in P and N range to prevent engine overheating. Unlike the vacuum-type VIS adopted in the Sorento, the Opirus adopts a DC motor-type variable intake system. Major components are a DC motor to change the length of the intake runner and MRS1 and MRS2 of Hall-type motor position sensors to detect the shutter position. The VIS operates in the range from 4,000 to 4,500 RPM in 9 steps, and it opens fully above 4,500 RPM. When the DC motor and MRS fail, they cannot be replaced separately, only as an ICV, in-duct control valve assembly. Let's take a look at the electronic throttle system. The ETS is also referred to as the drive-by-wire system. Eliminates the mechanical element. Improves drivability through accuracy of air intake control. Satisfies the strict exhaust emission regulation. Eliminates additional components for subsystems such as cruise control, traction control, and idle speed control. And increases serviceability and system reliability. Let's take a look at the main components of the ETS, which are ECM, ETS unit, throttle motor, fail-safe motor, TPS, APS, and ETS relay. The APS has 2 potentiometers used as APS1 and APS2. APS1 is used as a sub-signal to the ETS unit, and APS2 is the main signal to the ECM. APS has 8 terminals with an idle switch. Both APS1 and APS2 signals show the same data range from 0.45 volts at idle to 4.8 volts at wide open throttle. The idle switch output shows 0 voltage at idle and 5 volts off idle condition. The ECM is located at the center panel base, and its main functions are to calculate the target throttle opening, to generate the throttle motor activation signal to the ETS unit, to perform serial communication with the ETS unit, and to control the fail-safe function when the ETS system fails. The ETS unit is located below the passenger side dash panel. Its main function is to generate throttle motor activating current and feedback control of the target throttle opening. The main purpose of the TPS is to detect the throttle valve opening and feedback of the throttle motor position. A 2 potentiometer type sensor is used. TPS1 is the main sensor to the ETS unit, and TPS2 is a fail-safe sensor for the ECM. TPS1 ranges from 0.3 volts at idle to 4.7 volts at wide open. The TPS2 valve is opposite. It starts from 4.7 volts at idle and drops to 0.3 volts at wide open throttle. When the difference between the TPS1 and TPS2 valves exceeds 1 volt, the ETS switches to limp home function. A 3-wire brushless servo motor is used for throttle motor activation. There are 3 connections of W, U, and V with 4 phases. When U and W become low, and V becomes high, the motor turns right 30 degrees. Each coil's resistance is 0.6 to 1.5 ohms. If maximum resistance variation between the three coils exceeds 0.5 ohms, proper ETS operation cannot be guaranteed. The limp home mode activates the fail-safe valve when ETS problems are detected, such as throttle motor open or short circuit, throttle motor stuck open, TPS and APS fault, ETS unit fault, ETS relay fault, and RPM drop by electrical load. For any of the conditions above, the engine RPM is set to 1,500 to 2,000. Initialization has to be done in the following cases to learn the exact throttle motor position. After production in the factory, throttle motor replacement, throttle body replacement, TPS replacement, and after repairing an ETS problem. The procedures for initialization are follows. First, erase the trouble codes from the ECM and ETS units. Second, turn the ignition key on, less than 1 second. Third, turn the ignition key off until the main relay turns off, usually about 10 seconds. Finally, turn the ignition key on for more than 1 second to hold the throttle motor position. We've learned the Opirus engine so far. Now, let's move on to the automatic transaxle. The Opirus adopts the same 5-speed automatic transaxle installed in the Carnival 3.5-liter. Noise, vibration, and harshness levels were greatly reduced. The F5A51 consists of 4 clutches, 3 brakes, and 2 one-way clutches. Compared to the 4-speed automatic transaxle used in the Optima, a direct clutch, a reduction brake, and a one-way clutch for the sub-shift section are added. Compared to the 5-speed automatic transaxle used in the existing Carnival 3.5-liter, 4th gear ratio has been changed. This is achieved by using different operating elements in 4th gear from that of the Opirus. In the current 5-speed transaxle, the reduction brake operates through in 3rd gear and is released in 4th gear. To reduce judder when shifting from 3rd to 4th gear, the reduction brake remains engaged through 4th gear and is released in 5th gear. As a result, 4th gear ratio is increased and direct clutch operates only in the 5th gear. This new shift design will be applied to all 5-speed HiVec automatic transaxles in the future. It will also be applied to current production of the Carnival 3.5-liter. Other components, such as hydraulic control and electronic control, are the same with those of the existing transmissions. For more information, refer to the HiVec training module from Kia Motors. Now that we've learned about the Opirus automatic transaxle, let's move on to the chassis system. The ECS system used in some Opirus models is an electronic controlled suspension. The ECS improves the vehicle's ride quality from handling performance by controlling the vehicle's motions depending on road surface conditions and the driver's actions. This video shows the shock absorber damper characteristics of the electronic controlled suspension system, how ECS controls the suspension, and inputs and outputs. First of all, let's see the damper characteristics of the semi-active ECS system. A proportional solenoid valve is attached to the bottom of the shock absorber on ECS systems. Damping characteristics are changed based on the amount of current supplied to the solenoid. The amount of current applied to the solenoid controls the rotation of the pilot spool valve inside the shock absorber. The spool valve controls oil flow, altering compression and rebound feel. When applied current is 0.3 to 0.8 amps, the damping force in the compression stroke becomes soft, but damping force is hard during the rebound stroke. When the applied current is 0.8 to 1.3 amps, the damping force in the compression stroke becomes hard, and damping force is soft during the rebound stroke. When the applied current is 0.8 amps, the damping forces are soft in both rebound and compression conditions. Now, let's move on to the ECS control. The ECS system controls the vehicle's ride and handling. Ride control consists of controlling the vehicle's action during anti-bounce, anti-roll, and anti-pitch situations, and sensing road conditions such as bumpiness or smoothness during road judgment control. Ride control related to the vertical motion of the vehicle is regulated by the information from the vertical acceleration sensors, as well as the vehicle speed sensor. As for the control related to the handling, there's an anti-roll control, anti-dive control, anti-squat control, and speed-sensitive control. The anti-roll control uses the steering angular velocity of the vehicle's speed. Anti-dive control uses brake on-off information and the vehicle's speed signal, and the anti-squat control uses the TPS signal. Besides, the speed-sensitive control begins to apply when the vehicle speed is over 140 kilometers per hour, providing the hard damping force. Now let's learn about the ECS inputs and outputs. These are the primary inputs for the ECS. The alternator L terminal senses the alternator is generating enough power to run the ECS components properly. A brake switch to control the anti-dive. An ECS select switch to choose between normal and sport modes. Normal mode provides a comfortable ride, and the sport mode stiffens the suspension for better handling. A vehicle speed sensor for overall handling control. A steering sensor for anti-roll control. A TPS for anti-squat control. And 3 acceleration sensors for overall ride control. These are the primary outputs. An ECS indicator used as a warning lamp. An actuator relay, which supplies power to the solenoids. And 4 solenoid valves, which controls the damping force of the 4 shock absorbers. Let's look at the structure of the solenoid valve. The solenoid consists of an inner coil, spring, plunger, spool valve, and dampening control valve. 2 springs are located at both ends of the plunger and spool valve. Depending on the current applied to the coil, the spool valve may be moved by the springs. In this example, the spool valve moves to the left. Now let's see how the oil flows based on the position of the spool valve. When the applied current is 0.8 amps, the damping force is soft for both compression and rebound strokes. At 0.8 amps, the spool valve passageways are both open. The oil inside the rebound and compression chamber flows easily to the base chamber through the spool valve. When the applied current drops below 0.8 amps, the spool valve moves to the left as the force of the spring against the spool valve overcomes the dropping magnetic force of the coil. During the compression stroke, the oil flows from the compression chamber to the base chamber freely because the spool valve remains open. As a result, the compression stroke remains soft. As the spool valve moves left, the opening for the rebound chamber to the base chamber gets smaller, restricting oil flow. When applied current reaches 0.3 amps, the oil path is closed completely, and the rebound stroke becomes the hardest. If the applied current increases above 0.8 amps, the spool valve moves to the right, decreasing oil flow to the compression chamber. When current increases to 1.3 amps, the opening between the compression chamber and the base chamber is closed completely. At 1.3 amps, the compression stroke becomes the hardest. During the rebound stroke, the oil path from the rebound chamber to the base chamber through the spool valve remains open, so the rebound stroke remains soft. We have reviewed the semi-active ECS system used in the Opirus. Now let's move on to the ESP. The ESP provides improved driving stability relative to under and oversteer conditions. Further, the brake assist system, or BAS, is added to supply just the right amount of braking during these conditions. To better understand the ESP system in the Opirus, we'll explain about the ESP control module, inputs and outputs, and a brief introduction of the BAS. Let's look at the functions of the ESP control module now. The ESP control module is integrated into the ESP unit. It continuously monitors all electrical components and provides diagnostic help. The ESP control module helps maintain vehicle stability by effectively controlling understeer and oversteer. It also controls ABS and TCS functions. Let's study how the ESP controls the vehicle during understeer and oversteer conditions. Understeering, the vehicle does not steer as much as the driver intends, begins while the vehicle is turning. The vehicle slips outward, away from the direction of the turn, regardless of the driver's intention. Now understeer control starts. The ESP control module generates braking force at the inner wheel of the turn. The inner wheel pulls the vehicle towards the circle, correcting for understeer. On the other hand, if oversteering occurs while turning, the vehicle moves toward the direction of the turn too far. Now, oversteer control starts. The ESP control module generates braking force to the outer wheels. The braking action on the outer wheels pulls the vehicle away from the circle, correcting for oversteer. Now, let's review the inputs and outputs. The inputs of the ESP system are 4 active type wheel speed sensors, a steering angle sensor, a combination yaw rate and lateral acceleration sensor, 2 pressure sensors, a brake switch, and ESP off switch. As for the outputs, there's a motor pump, solenoid valves, ABS warning lamp, EBD warning lamp, TCS and ESP warning lamp, TCS and ESP function lamp, and CAN communication line with the power control module, or PCM. Now let's take a look at the new ESP wheel speed sensors. These new sensors are an active magnetic resistance type. When powered by 12 volts, the sensors generate 7 milliamps or 14 milliamps. The wheel speed sensor is located on the hub, and the air gap cannot be measured because of the sensor's protection cap. The ESP control module calculates the vehicle yaw rate based on the steering angle sensor signal and other inputs while turning. The calculated yaw rate and the actual yaw rate from the sensor cluster are compared together. The difference between the two valves is the basic factor to determine the vehicle's understeer or oversteer condition. The lateral acceleration sensor and the yaw rate sensor are important components of the ESP. The cluster links these sensors to an onboard computer unit and to a CAN interface The sensor cluster is mounted on the chassis under the center console. Its modular design concept allows future additional sensor functions. The pressure sensor shows the driver's braking intentions. When the brake pedal is not applied, the output voltage is 0.5 volts. And when the brake pedal is applied, the output voltage increases to nearly 4.7 volts. Let's learn about the BAS, Brake Assist System, used in the ESP. The BAS used in the Opirus ESP has extended logic to assist braking by driving the ESP hydraulic unit on demand. To operate the BAS, the following three conditions must occur at the same time. Braking pressure should exceed 20 bar. And pressure increase rate is more than 1100 bars per second, and the vehicle speed exceeds 7 kilometers per hour. When the BAS control logic recognizes that there's an emergency braking situation, the shuttle valve is opened and the TCS valve is closed. The ESP pump starts up and increases the braking pressure in a split second to a pressure level above the current driver-applied level. The ABS then keeps the individual wheels from locking up. We've seen the structure, inputs and outputs, and the BAS and ESP installed in the Opirus. Now let's move on to the electrical system. This section contains information about the Body Control Module, or BCM, Integrated Memory System, or IMS, High Intensity Discharge Headlights, or HID, Auto Leveling Device, Safety Power Window, Backing Warning System, or BWS, and Trip Computer. Let's take a look at these. The Body Control Module is brand new for the Opirus. The Body Control Module incorporates numerous electrical system functions, including ETACs. We will review the following systems in this section. General characteristics of the BCM. Wiper motor control. Lamp control. Turn signal and stop lamp control. Buzzer warning control. Keyhole illumination control. Defogger timer control. Room lamp delay control. Anti-theft function control, and self-diagnosis. The Body Control Module shares the information with each control module through CAN communication. The communication between modules, such as the Body Control Module, Driver's Side Door Module, Assist Doors Side Module, Power Seat Control Module, and Steering Wheel Control Module, uses a relatively new technology called CAN communication. Multifunction switch signals are transmitted to the Body Control Module with LIN communication. Let's take a look at the wiper motor control. The intermittent wiper control is controlled by the rain sensor. When the wiper switch is in the auto position, the signal is sensed by the Body Control Module using LIN communication. The Body Control Module transmits switch information to the rain sensor through pulses in the modulation signal. If the rain sensor senses rain in this condition, the rain sensor informs the Body Control Module through different pulses in the modulation signals. The intermittent operation, slow to fast, changes based on the amount of rain detected by the rain sensor. Perform self-diagnosis as follows when the wiper motor does not operate smoothly with the rain sensor signals. First of all, turn the ignition key on and set the wiper switch to the auto position. Then the wiper motor operates once. Move the intermittent volume adjuster switch to step 5. Adjust the switch down to step 4. If the wiper operates, it's fault A. Move the switch down to step 3. If the wiper motor operates, it's fault B. If the wiper motor operates when the switch is down to step 2, it's regarded as fault C. The wiper motor may not operate as expected if there's a breakdown in the LIN communication. If this occurs, an additional low-speed wiper relay can be driven by the BCM to ensure wiper operation. When the lamp switch is turned on, the switch signal is transmitted to the body control module through LIN communication, activating the lamp relay to turn on the lamps. A headlamp low relay is controlled directly by the headlamp switch in case the lamps don't operate due to LIN communication problems. The tail lamps can be automatically turned off using the auto cut function. If the ignition key is removed and the driver's door is opened when the tail lamp switch is on, the tail lamps turn off automatically. If the driver's door is closed and the ignition key is inserted, the tail lamps turn on again, assuming the lamp switch is in the on position. By the way, the tail and headlamps can be controlled by the auto light sensor too. When the lamp switch is in the auto position, the auto light sensor senses the ambient light condition and activates the lamps. The lamps are turned off or on based on the sensor's output voltage to the control module. The turn signals are now controlled by the body control module. When the turn signal switch signals the BCM through LIN communication signals to activate the turn signals, the BCM controls turn signal relay operation. The hazard switch is input directly to the BCM through standard wiring. When the brake pedal is pressed, battery power is supplied to the body control module and the brake lamps turn on. If the brake lamp fuse or any of the lamps are burned out, the failure indicator in the instrument panel turns on to inform the driver of a malfunction every time the driver presses the brake pedal. If the ignition key is removed from the cylinder and the driver's or passenger's door is opened, the keyhole illumination lamp turns on. If the door is closed again, it remains on for 10 seconds. The defogger timer controls rear window and outside mirror defogging at the same time. If the defogger switch is depressed when the engine is running and charging based on the alternator L terminal signal, the body control module grounds the defogger relay, turning on the rear defogger. The BCM sends defogger switch signals to the driver's door module and the assist door module using CAN communication. These two modules then activate the heater controls from the outside mirrors. If the door is opened when the room lamp switch is in the door position and the ignition key is turned off, the room lamp turns on. If the door is closed, the room lamp fades out slowly for 5 seconds. If the unlock signal of the transmitter is received when all doors are closed, the room lamp remains on for 30 seconds. Since the anti-theft function is the same as the existing e-tax, let's briefly review some anti-theft characteristics only. To review, there are 3 different kinds of input signals related to the anti-theft function. These signals are direct input signals through CAN communication, and transmitter signals. Direct input signals are all the door switches: the trunk open switch, trunk unlock switch, hood switch, and the key in switch. Door lock and unlock switch signals in the door actuator are transmitted to the body control module through CAN communication from each door module. If the RKE transmitter is lost after the alarm has been put into the armed condition, it can be disarmed using the ignition key. If the door is opened with the ignition key, the alarm activates. Turn the ignition key on and wait for 30 seconds. After 30 seconds, the alarm should stop and the alarm is disarmed. Let's look at the key registration now. Basically, only 2 keys can be registered using the HiScan Pro. First, connect the additional adapter connector to the self-diagnosis connector of the HiScan Pro. Turn on the HiScan Pro after connecting it to the RC connector. Select code saving in the body control module system on the HiScan Pro. Follow the instructions as shown on the HiScan Pro screens. Just a word or two about body electrical self-diagnosis. First, connect the HiScan Pro to the self-diagnostic connector. When the body control module is selected with HiScan Pro connected and operating normally, you can perform the usual HiScan Pro functions. Check for self-diagnosis codes, observe input and output signals, and run actuator tests. We have learned about the body control module functions of the Opirus so far. Next, let's look at the integrated memory system. The integrated memory system memorizes and replays up to 2 driver's seat, steering wheel, and outside mirror positions. To review the system function first, power steering, outside mirror, and power seat can be operated manually by the adjust switch, and memory function is available to memorize and replay 2 positions. I'd like to review the input, output, and characteristics for this system. Input signals for the CAN communication are memory position switch 1, memory position switch 2, stop switch, and memory switch. More inputs are the shift lever parking position, reverse signal, and vehicle speed signal. These are all inputs to the body control module through CAN communication. The power seat control module has several sensors and switches. Here are the front and rear height sensor to sense the height of the front and rear of the seat cushion, a sliding sensor to sense the front and rear position of the seat cushion, and a recliner sensor to sense the seat back position. The limit switch is an on-off type switch. It limits forward and rearward travel when the switch is tripped during operation. The steering wheel control system has 2 sensors to sense the steering column tilt and telescope positions. These are potentiometer type sensors, where voltage changes from 0 to 5 volts by the component's position. This information is input into the steering column control module. This system controls 3 functions. These are seat replay using the memory switch. Outside mirrors pivot downward 5 when the shift lever is in the R position. Seat position replay function by keyless transmitter. When the position of the seat, steering wheel, and mirror is memorized, the positions are automatically replayed when memory switch 1 or 2 is pressed. To memorize the position, first of all, turn the ignition key on. Adjust the positions of the seat, mirror, and steering wheel using the appropriate switches. Press the M switch. Select the switch to memorize. Then it is memorized. As for outside mirror control, if the shift lever is moved to the R position when the ignition is on, the outside mirror pivots downward 5 degrees. By the way, mirror action is different depending on mirror selection switch position. When the mirror selection switch is in the center position, the outside mirrors do not pivot. If positioned in L, both mirrors operate. If positioned in R, only the right-hand side mirror moves. And then the shift lever R position signal is transmitted to the driver's and passenger's door modules by the body control module. The mirror select switch position is transferred to the assist door module from the drive door module. The seat position, and only the seat, is memorized with the keyless entry transmitter. If the lock button of the transmitter is pressed with the ignition key removed, the seat position is stored when the ignition was on. Then, if the seat position is changed when the ignition is turned off, the seat will return to the previous position when the transmitter unlock button is pressed. RKE transmitter signals are input to the body control module and transmitted to each control module through CAN communication. When the battery is disconnected or the IMS controller is replaced, memories will be erased. When the control module is replaced, it does not require initialization or resetting. Let's look at the HID and the auto-leveling device of the Opirus vehicle. The HID headlamp operates with a totally different concept from the halogen lamp. For the headlamp leveling to keep constant headlamp level at all times, a headlamp auto-leveling device is installed together. We'll explain about the HID headlamps such as components and operation of the HID headlamp, a circuit diagram and cautions, components and operation of the auto-leveling device, input and output signals of the auto-leveling device, and diagnosis. The baluster increases the voltage to high when supplied with 12 volts. High voltage generated is transformed to the igniter through a high voltage cable, and the igniter transfers the high voltage to the bulb to generate the light. For the high voltage supplied to the HID headlamp device, an ignition point of 20,000 volts is generated for 525 milliseconds for the ignition when 12 volts of power is supplied. And voltage drops to 85 volts after ignition to supply the power with a frequency of 400 Hertz. Since the HID headlamp device operates with high voltage, the following special precautions should be exercised for maintenance. To repair the headlamp or adjacent parts, the switch must be turned off. Do not turn the headlamp switch on when the headlamp igniter connector is removed. When replacing headlamp bulbs, use bulbs of the same maker in both sides. Do not recommend direct bulb replacement by customers. Let's see the components and operation of the auto-leveling device. The control module senses the change in vehicle height and calculates the head angle to be adjusted. When voltage is applied to the headlamp leveling device, the headlamp leveling device actuator adjusts the headlamp angle. The sensor and control module senses the vehicle height change by the vehicle load and calculates the leveling amount, which senses the height of the rear lower arm. The auto-leveling actuator receives the adjusting voltage from the sensor and control module and adjusts the leveling. As for the operating conditions of leveling, leveling activates when auto-leveling is required due to vehicle height change when the ignition and headlamp are on. If the level sensor changes more than 2 degrees before the vehicle departure, the headlamp leveling is made 1.5 seconds after the departure. If the vehicle height changes more than 2 degrees while the vehicle is in motion with the speed of 4 kilometers an hour or above, and this condition continues longer than 5 minutes, the headlamp level is compensated. This system needs to be reset when the sensor and control module is replaced. Reset is made under normal tire pressure on a flat surface while unloaded. To reset, do communication with the auto-leveling device by high scan and select Reset from the high scan menu and press Enter. Then it is set automatically. As for the input-output signals of the auto-leveling device operation, the headlamp turns on as the battery power is supplied to pin number 2 from the ignition key. Then pin number 6 drops to 0 voltage from 12 volts, and the calculated adjustment voltage is supplied to the actuator through pin number 7. If the vehicle speed signal and height sensor level changes through pin number 4 while driving, the actuator drives within the operation condition range. When the system fails, it can be checked with high scan. To list the diagnostic trouble codes, they are ECM hardware errors, ECM software error, 0 setting is not done, headlamp switch signal is open, vehicle speed sensor malfunction, and actuator control signal line open or short. The values of the input-output signals can be read in current data. Here, the current actuator value stands for 80% of battery voltage supplied to the actuator. In other words, 12 times 0.8 equals 9.6 volts of input voltage is the leveling voltage to the actuator. And the compulsory actuator adjustment can be made. Select Actuator Adjusting and adjust the value compulsory to be 15 through 80%. Then actuator operation can be checked. We have learned about the HID headlamp and auto leveling device so far. Let's look at the safety power window system. For the convenience and safety, safety power windows are installed in all windows. The power window main switch, DDM, on the driver's side and power window assistance switch, ADM, on the passenger side do CAN communication with each other. On the contrary, the power window switch and safety window module do LIN communication. If the driver operates the driver's side power window switch, the safety window module receives a signal to operate the window motor. While the window is moving up automatically, if any foreign object is caught in the window, the sensor in the power window motor senses this and drops the window 150 millimeters automatically. Let's see the sensor wave using high scan now. If the window operates as shown in the screen, the sensor in the power window motor fails or the line is short or open. Then it has to be repaired. In addition, if the safety window module or power window motor is reinstalled, the system must be initialized. To do that, operate the switch continuously for about 0.5 seconds more after the power window is up completely. If the system is not initialized, auto up will not be done in the window. We've learned about the safety window of the Opirus so far. Now, let's learn about the back warning system. If no obstacle is behind the vehicle when the shift lever is placed in R to move back, the buzzer sounds once. The warning sounds in 3 stages depending on the distance to the obstacle. This system consists of 4 supersonic sensors in the rear bumper, the control module, and buzzer. When the shift lever is placed in the R position, battery voltage is applied to the inhibitor switch. Then 8 volts are inputted from the controller to the 4 sensors and transmission of the supersonic wave generates. If an obstacle is sensed, the transmission is made again and the controller makes buzzer sounds. As for the sensing, the sensor generates the supersonic wave and receives the wave again to determine the distance to the objects. When the shift lever is placed in R position, the buzzer sounds once if it's normal. Depending on the distance to the obstacle, the buzzer sounds every 340 milliseconds if the obstacle is within 120 centimeters, and it sounds every 170 milliseconds if the obstacle is within 80 centimeters. and it sounds continuously if the obstacle is within 40 centimeters to inform you of the distance. If the sensor fails, it can be diagnosed. When the shift lever is placed in R, if it does not sound, 12 volts of R signal may not be inputted. If the buzzer sounds 3 times every 300 milliseconds, determine it to be sensor line failure and perform self-diagnosis. Place the shift lever into the R position when the ignition is on and place the self-diagnosis switch on. The buzzer sounds differently by sensor failure types. When the side left sensor fails, the buzzer sounds once every 750 milliseconds. When the rear left signal fails, it sounds twice every 750 milliseconds. When the rear right sensor fails, it sounds 3 times every 750 milliseconds. When the side right sensor fails, it sounds 4 times every 750 milliseconds. Be aware that this system cannot sense a failure in the following cases. When approaching a curved obstacle, supersonic wave is reflected. A narrow obstacle like rope or string. Change of vehicle height is serious due to a heavy load. When driving back at the declined load, foreign material is attached to the sensor. And an obstacle absorbing the supersonic wave like cotton or snow. Example, fire plug covered with snow. The trip computer displays the information on the LCD display to inform the driver of information such as travel time and radio frequency that are obtained during driving. This videotape contains general information on the trip computer, input of the trip computer, and output of the trip computer. Whenever the trip switch is pressed to get the trip computer information, it shows trip computer information in the sequence of ambient temperature, distance to empty, driving distance, average speed, average fuel consumption, momentary fuel consumption, driving time. When the trip switch is pressed longer than 1 plus or minus 0.1 seconds, the motor turns off. If the trip switch or reset switch is pressed again, then the monitor turns on. If the reset switch is pressed longer than 1 second, the trip computer is zero set. However, ambient temperature, distance to empty, and momentary fuel consumption is not zero set. If the reset switch is pressed in the ambient temperature mode, it converts from Fahrenheit temperature to centigrade temperature and vice versa. Now let's see input specification. To review the main input signals of the trip computer information, it determines the engine starting by receiving the alternator L terminal signal. The vehicle speed signal is inputted from the vehicle speed sensor. The engine control module inputs the injection signal. This signal recognizes the average fuel consumption, assuming 80 milliccs of fuel is injected per pulse. The input signal from the fuel sender is informed of fuel information in the fuel tank by the voltage change divided in the fuel sender. The fuel cap open switch is a signal to determine refueling. If the fuel cap is opened, battery voltage is inputted. It judges fuel charging when the signal is present and the fuel sender changes. The ambient sensor is installed in front of the radiator, and it gets information of ambient temperature with the voltage change when the ignition is turned on. As for the output information, I'd like to briefly explain only trip computer information displayed by calculating input signals. The displayed output information of the trip computer are distance to empty, driving distance, average vehicle speed, driving time, ambient temperature, average fuel consumption, and momentary fuel consumption. Distance to empty shows the distance that can be driven with the remaining fuel. If the estimated data is below 50 kilometers or 31 miles, you'll see no data or dashes displayed blinking on the LCD to inform the driver of the fuel charging. Driving distance shows the distance driven from the data reset. The average vehicle speed shows the average driving speed from ignition on to off. Accordingly, it stands for the average speed only when the vehicle speed signal and the engine on signal are inputted. Driving time shows the accumulated driving time from ignition on to off. The ambient temperature is displayed by converting the voltage signals from the sensor. It's displayed at the interval of 0.5 degrees Celsius per 90 seconds when the temperature increases. When the temperature decreases, it's displayed at the interval of 0.5 degrees Celsius per 2 seconds. When the sensor or wiring harness fails, you'll see blinking dashes displayed instead of data to inform the driver of a failure. Average fuel consumption is obtained by dividing the injection amount with driving distance. Driving distance and injection amount for every second are checked accumulatively and displayed. The data calculation formula is to divide the injection amount with driving distance. Kia Motors has been doing its best to promote effective after-service. And we will continue to do our best to meet your after-service needs by providing various training materials. Kia will make an effort to continuously produce the best in class in terms of quality, design, and performance. Thank you.